So thanks for your attention. I'm going to talk about our new project for the coming academic year. So a lot of what we do, we make lasers. We make industrial lasers. These are used in factories all around the world. Our biggest customers are in Europe and China. I'll tell you a little bit more about the company, and then I'll talk about the project itself. The project is focused on helping us make better lasers. Our lasers are used for making all kinds of stuff, from keychains to heavy industrial uses. All of that depends on us delivering a very consistent, high-quality product. And so this project is really focused on helping us achieve that goal. So we're up in Uxbridge, Mass. It's a small town, kind of out in the suburbs. This is we're the only occupant in this facility. We just moved in here about a year and a half ago. So we're upgrading the company quite a bit. We've achieved certain milestones recently. We've got ISO certification, and we're a rapidly growing company. As I said, we ship globally. We do have customers all over the world, from South America to many Asian countries. So we're a truly global company, but we're still pretty small. We're only about 55 people total. So it's still a good environment where you would get to work with both the engineering team, the production team, and kind of see all sides of a small company. As Harish said, I'm the Chief Technology Officer at iRadian. I've been in the laser industry for about 20 years now. I have a PhD in optics from University of Central Florida. So I'm very deep in lasers. And what we try to do is have a very balanced team. So we have laser engineers, we also have mechanical engineers, we actually have some URI alumni on our staff, engineering staff, mechanical and laser engineering. We also have RF engineering. We don't have a whole lot as far as computer engineering, computer science, and so this is an area where we're always looking to bolster our capabilities in-house. So we're small. I mentioned we ship about 3,000 lasers per year, which is a pretty good number for an industrial laser company. But despite our size and modest settings, we do intend to become the #1 laser supplier in the world for this type of what we call radio frequency driven carbon dioxide lasers. So the laser works by energizing a gas mixture. The primary constituent is carbon dioxide, and that emits laser radiation out in the infrared, and that's what is used for all the different applications. So it's a it's kind of an old technology. It's actually been around since the 1960s, but it's still very dominant in the laser industry, and there's a lot of really interesting physics that goes on inside the laser. I won't go too deep into that tonight, but it would be something that you would get to learn if you were to come work on this project with us. So these are what the lasers look like. There's a bunch of them on racks ready to ship out the door. They're about yay big, about big as a bread box, weigh maybe 40, 50 pounds. They go into much larger machines that manipulate the beam as well as materials. In some cases, they go on the end of big robot arms which move the lasers around. It's really cool to see in action in a factory. This is our production floor. We do some of our work in a clean room. This is a vacuum station where we evacuate and fill the laser. So a lot of interesting equipment you might not see in other environments. Depending on classwork you take here, you might not get access to those. So it would be a learning environment in a number of ways. Our laser, I said, is about this big. This is one machine, one of our large customers, Trotec. They use it. You can't see it in the picture, but the laser would be strapped onto the backside. And this is kind of like a flatbed engraving marking machine, kind of about the size of an old-fashioned copier. And so people, our customers would put materials from wood to pens, glass, all kinds of objects in the flatbed area, and the machine would scan the laser beam over the material to do things like carving stamp rubber for stamps, making in this case, a smartphone cover. A lot of consumer goods are made this way. A lot of our lasers go into food industry. When you look at a date code on a can, a bottle, an orange, that's all done with the CO2 laser. So that's how common these lasers are in usage. You don't necessarily know how those marks get on your food or your consumer goods. A lot of it comes from a CO2 laser. So this video is going to show you, this is a promotional video, it's just going to show you some of the processes in action. So the beam is actually coming down through this head here. There's a lens that focuses it down onto the material. This little thing over here is a proximity sensor, so it's telling the whole system how close it is to the plane of the material. So this is typical speed. I mean, this isn't necessarily the highest value application we sell lasers into, but it shows you the kind of precision and speed you can achieve. Imagine trying to do this by hand or even with some kind of punching machine. You would never achieve the level of precision as you can with a laser like this. This is actually a fairly new application for lasers. You've seen more and more textiles with different stylations like these stress marks on them. What you're actually seeing here is in real time the laser beam is scanning up and down as it moves across the denim to create those stress marks. This is something that used to be done chemically with bleach or other stuff like that. But it's very hazardous to deal with those chemicals and also very slow. So you can actually do this much quicker now. So companies like Levi's they're converting completely over to laser processing for this type of effect. They've even said that they're moving to put the laser machines like in shopping malls, in department stores, so you can actually come in with your pattern or tell them what you want and they'll print it right on your jeans or whatever you're buying. So that's balsa wood. A lot of these applications aren't so obvious up front that you need a laser to do them, but when you do what we talk about a lot in marketing this type of technology is you do a return on investment calculation. And oftentimes the revenue, the profit comes down to a matter of seconds for operations like this in a factory. And that's where a laser technology like this really pays off. So this is acrylic, 2 millimeter acrylic that it's cutting through. So the beam, you can't see it because it's in the far infrared. It's actually at a wavelength of 10.6 microns, which is so far out, our eyes don't even pick it up as a faint glow or anything. So to us, the laser beam is completely invisible, but it's being focused down from that nozzle there onto the plexiglass. This is the laser cutting through sheet metal, steel, creating that spiral pattern. A lot more fireworks when you're cutting metal. This is pretty thin metal. I've worked with lasers, not at Iradian, at a previous company, that would actually cut through 2-inch thick steel. I mean, really high power stuff that used to only show up in like science fiction movies. Really quite an interesting world in industrial lasers. So this is called laser damage art. These little pixels, or I guess volume pixels, voxels, are being created in the middle of a transparent block, either glass or acrylic, and you create these little damage spots that scatter light and give you a nice artistic rendering. So kind of as a 3D image. So this is one of those marking applications where each bottle is getting a code, usually something like a date and location of where it's made. The cool thing is this is happening 600 bottles per minute, so these things are just flying down the conveyor belt and the laser's scanning and putting a number on it in real time. So this is an artistic print. So this is sort of thing where you would probably order online. You know, you upload a picture or you tell them what you want, and they'll put it onto some kind of unique background or some kind of unique canvas per your order. A lot of that is done, again, behind the scenes. You don't necessarily see this everywhere you go, but more and more it's being done by lasers. Okay, so looking at those applications, just imagine, if you will, if you had a laser that had a lot of power variations, or you take one laser out of the machine at the end of its life, you put a new one in and it's not the same. Those are issues we deal with in making these lasers, where lasers can be unstable if they're not made well, or you make a replacement, or you have to make 50 machines and have them all work the same, but the lasers are a little bit different unit to unit. Those are all issues that we deal with that we're trying to address partly with this project. So the level of precision we have to use to put these lasers together is on the micron scale. Just for frame of reference, this is a scanning electron microscope image of a typical human hair, about 150 micron diameter. And so the precision we use to put the lasers together, we're usually doing positional tolerances of about 50 microns. When we're aligning like mirrors and stuff inside the laser, we have to have precision similar tens of microradians. So very, very small errors in the way we put these lasers together have profound effects on the laser performance. So the idea for this project is to build something not fully automated, but something much easier to use than like old-fashioned gauges or micrometers and that sort of thing, where we're doing mechanical measurements. It's now very common for people to use 3D scanners, different types. There's laser scanners, there's structured light. Some of you probably have a phone that has that kind of technology that does facial recognition. It's all based on similar type of technology of using optical scanning technique. So what we want to do is use that to inspect some of our subassemblies, make sure that they're precisely aligned such that when they're put together in a big laser, the laser is nearly complete at that stage and requires a lot less hands-on tuning. So we talk a lot about GDT, the geometry, dimensioning, and tolerancing. And so these are the kinds of things that we want to inspect on our subassemblies using an optical inspection technique. So in principle, it's pretty easy to get up and started. Get started. We want to buy an off-the-shelf 3D scanner. You would be the ones helping us select that scanner, so understanding what it needs to do and then identifying the most cost-effective approach. Then start playing with it, understanding how it interacts with different objects, what kind of data you can get from it, and then the next step would be creating the comparison. So we have our solid model files that we generate in SolidWorks. They have all the tolerances and everything built into the file. So to compare that with the piece on the workbench and either give us pass-fail criteria and an error report. So in principle, it's pretty simple, one step after another. At the end of the day, it gives us an extremely valuable workstation, helps us build much better lasers, and gives you an opportunity to work with some state-of-the-art technology. So this is just a picture of a common 3D scanner where you literally just put the object within the scan area. It generates a 3D rendering. It can do all kind of interesting processing with that information. We actually had a demo 3D scanner in just to see, would it give us the right ballpark information we need. And so this is the 3D drawing of the piece. So these are two mirrors that are used inside the laser cavity in a metal housing. And then this is the 3D scan showing us relative depth of these surfaces to the rim here. This mirror is perfectly flat. This one is curved, so it's a concave mirror, which is by design. That's what it should be. And so for us, what we'd want to do is then have the program that you would work on take these measurements of angles and positions of these mirrors, compare them to the model, and generate an error report and a pass-fail criteria. Make sense? Okay, so that's the description. I'm happy to take any questions you have. I think I have a little bit of time.